the product of sums is greater than the sum of the products. This inequality is known as the Cauchy-Schwarz inequality. So say you have two sets of numbers. So you have set A, which is A1, A2, A3, all the way to AN, and you have set B, which is B1, B2, B3, all the way to Bn. Now, Cauchy-Schwarz states that A1 squared plus A2 squared plus A3 squared all the way to AN squared times B1 squared plus B2 squared plus B3 squared all the way to Bn squared is greater than or equal to A1 B1 plus A2 B2 plus A3 B3 all the way to AN Bn all squared. The product of the sums is greater than or equal to the sum of the products. Now let me show you an example of this inequality. If a plus b plus c is equal to 4, what is the minimum value of 1 over a plus 1 over b plus 1 over c? Well, at first, the application of Cauchy-Schwarz is not very obvious, but after some thought, notice that x times 1 over x is equal to 1. So what if the terms in our sets were root a, root b, and root c, and the terms in the other set were 1 over root a, 1 over root b, and 1 over root c. Now, I take the root because we have to square all the terms inside this inequality. Let this be set a, and let this be set b. So then, we get a plus b plus c, 1 over a plus 1 over b plus 1 over c. There are no square roots because we square each term, and so we get a, b, c, 1 over a, 1 over b, and 1 over c. This is greater than root a times 1 over root a is equal to 1, root b times 1 over root b is equal to 1, and the same for root c. So we get 1 plus 1 plus 1 all squared. So then we have a plus b plus c times 1 over a plus 1 over b plus 1 over c is greater than or equal to 3 squared, which is equal to 9. Now notice that a plus b plus c is equal to 4. So we have 4, 1 over a plus 1 over b plus 1 over c is greater than or equal to 9. But then we can divide both sides by 4 to get 1 over a plus 1 over b plus 1 over c is greater than or equal to 9 over 4. So the minimum possible value of 1 over a plus 1 over b plus 1 over c is 9 over 4, and so we are done. Now on to some applications of the Cauchy-Schwarz inequality. Alright, and now our first problem is on the board. So the first thing is we look at the first equation. So a plus b plus c is equal to 2, then a plus b is equal to 2 minus c. Now also, if a squared plus b squared plus c squared is equal to 12, then we also have it that a squared plus b squared is equal to 12 minus c squared. So then consider these two sets for our Cauchy-Schwarz. We have a, b, and 1, 1. So then, plugging these two sets into Cauchy-Schwarz, we then get a squared plus b squared times 1 plus 1 is greater than or equal to a times 1 plus b times 1 all squared. So then we get a plus b all squared. Remember, we are looking for solutions to c. So now we substitute 12 minus c squared into a squared plus b squared to get 12 minus c squared. Also, 1 plus 1 is equal to 2. So this is a 2. And then a plus b is equal to 2 minus c. So we get 2 minus c all squared. So now we can start expanding. We get 24 minus 2c squared is greater than or equal to 4 minus 4c plus c squared. And we can move these two terms over. So we get 3c squared minus 4c minus 20. And now I'm going to save time by just telling you that this factors into c plus 2 and 3c minus 10. So then, c is either equal to negative 2 or 10 over 3. Now 10 over 3 is larger than negative 2, so we subtract negative 2 from 10 over 3, and so 10 over 3 minus negative 2 is equal to 16 over 3. And so we are done. Alright, and now on to the next problem. Alright, and now our problem is right here. So you may first look at this problem and be extremely confused, as in what are you supposed to possibly do with all of these cotangents? But let's draw a diagram. So let's say we have a triangle. Now let's draw its incircle. But remember that a line drawn from a vertex to the inner radius bisects it. Drawing a point from the inner radius to the vertex gives us an angle bisector. But remember that we can always draw a radius perpendicular to an edge. So here we draw a radius perpendicular to edge AC. And so now we look at the cotangent of angle A. Now you see, the tangent is equal to the opposite over the adjacent, but the cotangent is equal to the adjacent over the opposite. So let's call this point here to be D. Then let's also call the inner radius to be O. So we are looking for the ratio AD over DO. But we already know that DO is equal to R, or the radius of the incircle. So we have AD over R. Now to find AD, let's connect OB. Now we know that DC plus CB is equal to the semi-perimeter, or half of the perimeter. We also know that AD is equal to DC, and we also know that we can call the line BC A. So AD is equal to S minus A, and then we divide it by R. And since we are squaring the cotangent of A over 2, we can square all this. Remember that since it is A over 2, we take half the angle, or the angle bisector. So then, applying the same logic to B and C, we then get S minus A over R all squared, plus 4 S minus B over R all squared, plus 9 S minus C over R all squared is equal to 6S over 7R squared. So then we notice that all the denominators have R, so we can cancel out all of the R's. So here we have S minus A squared plus 4 times S minus B squared plus 9 times S minus C squared is equal to 36S squared over 7 squared. And 7 squared is equal to 49, so we get 36S squared over 49. Now we can divide everything by 36 to get S minus A squared over 36 plus S minus B squared over 9 plus S minus C squared over 4. And this is also equal to 36S squared over 49. But one more thing, notice that 49 is equal to 36 plus 9 plus 4. And because this is true, we can then apply Cauchy-Schwarz to this equation. The first set is going to be 6, 3, 2, and the second set is going to be S minus A over 6, S minus B over 3, and S minus C over 2. So then we can put this into Cauchy-Schwarz to get 36 plus 9 plus 4 times S minus A squared over 36 plus S minus B squared over 9 plus S minus C squared over 4 is greater than or equal to S minus A plus S minus B plus S minus C all squared. And we have 3 semi-perimeters and 1 perimeter. So then we have 3S minus 2S, which is equal to S squared. So then we can divide both sides by 49 to get that S minus A squared over 36 plus S minus B squared over 9 plus S minus C squared over 4 is equal to S squared over 49. We then realize that S minus A is proportionate to 36 and S minus B is proportionate to 9 and S minus C is proportionate to 4. Notice that A is equal to the perimeter minus B minus C, so A is equal to S minus B plus S minus C. So then we can subtract this to then turn this equation into negative S plus B plus C is equal to 36. Now let's solve for this system of equations. So first, notice that if we add these two together, we get 2S minus B minus C. Now, as I said earlier, the perimeter minus B minus C is equal to A, or 2 times the semi-perimeter minus B minus C is equal to A. So adding these two equations, A is then equal to 13. S minus A is equal to 36. S minus 13 is equal to 36. S is equal to 49. And so we have the semi-perimeter. So then we can substitute S into these two equations to get 49 minus 9 is equal to B, and 49 minus 4 is equal to C. So B is equal to 40, and C is equal to 45. So now the triangle that has properties similar to the triangle in the problem will have side lengths proportionate to 13, 40, and 45. And so that is our answer. And we are done. Alright, thanks for watching. Hopefully you enjoyed, and hopefully I'll see you next time.